Hello and welcome to our discussion on polar coordinates. These are the topics we're going to cover, and as always, if you want to fast forward to the topic you need to review, feel free to do so. This slide will come up as we go from topic to topic. First, some lovely vocabulary. So we're used to dealing with things in the Cartesian plane, the rectangular coordinate plane. Well, now we're going to be dealing with things in what's called the polar coordinate plane, and it's really very similar. It's the idea of describing a distance in inches versus centimeters, right? It's still a distance. You just give it two different names. And it's kind of the same thing here. You can designate the location of any point in the rectangular coordinate system by telling someone its x and y distance, right? Give it its x and y coordinates. Well, we can do the same thing with polar coordinates, but instead of doing an x and a y, you have an r and a theta, where r is a distance with direction, right? It can be plus or minus, basically means you're going either forward or backwards. And then theta is just your angle of rotation. So basically, you can think of standing in the middle of a field, and the middle of the field is the origin, right? What we normally think of as the origin, only now they're going to call it the pole or the polar axis. And that's just the center of your coordinate plane. And if you wanted to tell somebody how to get to a certain point in that field, you would tell them to rotate a certain degree, right? Face a certain direction and then walk forward. Or you could have them face in the exact opposite direction and walk backwards. And that's basically what polar coordinates are, is it's those kind of directions. You can tell them how to get to a certain point by facing in a certain direction and then either walking forward or walking backwards. So here's kind of a visual of what's going on, right? Here's our point that we would normally think of as having an X and a Y, but instead you're starting here at the center of the field, right? You're at the pole, which is, what we can think of as the origin. And you tell somebody, okay, turn left, right, by a certain degree, theta, and that's going to be positive because remember positive is in the counterclockwise direction. And once you rotate to that correct kind of direction, walk forward by this distance r. Or you could have had them spin all the way around till they were looking over here in this direction and then walk backwards that distance of r. So any point in the plane can be thought of in both ways. All right, so let's look at a typical kind of something that we're used to seeing. Here are our axes, all right? We start here in the center, and if we want to get to this point here, well, normally we would describe that as x, y, right? Where we've got that height y and this distance x, and that's how we would tell people where that point is. But we can also think of just shining a flashlight or a laser or something and somehow figuring out what direction that point is from the origin. That becomes our theta, right? Our direction that we have to rotate in order to shine the light on that point. And then this is the overall distance that the light would have to travel, right? Or we would have to walk to get there. Or we could go either reverse, right? Go a negative theta or all the way around to this direction. But in either way, if we're facing now in this direction and then walk backwards, it's the same thing. Okay, so that brings up the point of there are always going to be multiple ways, in fact, infinitely many ways of representing the same point. Just like we can spin around a circle when we're talking about trig stuff. We can go pi over 2, but then we can go 2 pi plus pi over 2, and we get basically to that same orientation. The same problem happens with polar coordinates in that you don't have just a unique solution for a point. every point in the plane has infinitely many solutions. That's the one drawback to polar coordinates. That's the one kind of nice thing about the Cartesian plane is every point in the plane has one and only one, right? There's an x and a y pair that tells you where you are, and there's no other xy pair that matches that point. But in polar coordinates, you can designate that point infinitely many ways by basically just going around the circle more than once, right? Instead of doing the green angle here, we could do a blue one where we go all the way around 2 pi plus whatever theta is, and that gets us the same orientation. And then, of course, we can play this game all day long, and we can go around 4 pi, 6 pi, 8 pi, a million pi, so on and so forth, and then just add that little bit, and we're always back to the same place. And then, of course, the same thing in the negative direction. Okay, so that's the one downside to polar coordinates. All right, so here's an example of how we can plot a point with these coordinates, 3, 225. Remember, 3 is the distance. We're going to go out a distance of 3 units, and we're going to go in the positive direction. So we're going to move forward whenever we orient ourselves. And then 225 is going to be the angle at which we orient. And we can show how we can do that 3 different ways. We can do it and let r be a negative number. And then put the angle between 0 and 360. We can let r be a negative number and let the angle be a negative, right? So it's between negative 360 and 0, so it just means we're going in the opposite direction, clockwise. And then we can also do that with r being greater than 0 and going negative. And then, of course, the first example, A, is when r is positive and we're between 0 and 360. So it's kind of the 4 ways we can do it. At least the 4 simple ways, and then we can do it with multiples of 360. So here's the standard way. We start at the x-axis, we go 225 degrees, then we go forward 3 units, we're done, right? Now if we want to do the same thing where r is negative, i.e. we have to walk backwards, then instead of facing in this direction, we have to be facing in that direction. So you have to figure out what is this angle here. And you go, well, if this is 225, then you know, right, to here is 180. And so the leftover piece is 45, and that's how we know we go up 45 and then walk backwards. Simple, right? All right. The other two, same way. If we want to, again, walk backwards, right? So we have to face, instead of facing down here, we have to be facing up to the right. Then we have to move in a negative direction until we're facing in this direction. And as we saw before, this was a 45-degree angle. So of course, 360 minus 45 is 315. So we go the 315 degrees in this direction. That gets us oriented in the same exact direction. Go backwards by 3, done. Easy. If we want to let r be positive, so we now need to face in this direction so that we can walk towards the point instead of back up, right? And we want a negative angle, then instead of going around here to 225, the leftover bit, right, if you do 360 minus 225, you get 135, and that just means we do 135 in the other direction, which is a negative direction, and then we walk forward by 3. Okay, so have we beaten this dead horse, right? You get the idea that we can do this over and over and over again. We can orient ourselves in the direction we need to go or exactly 180 degrees off of the direction we need to go, and then we can walk forward if we're oriented in the right direction, or we can walk backwards if we're oriented 180 degrees off. Okay, on to the next idea. How do we convert back and forth? Just like 2.54 centimeters equals an inch, which allows us to go back and forth between inches and centimeters, there has to be a way to convert back and forth between polar and rectangular, because as we've seen, it's still a point in space, and if we can represent it both ways, then there has to be a way to represent those things equally and somehow have a bridge between the two. You kind of think of it as like two different languages or two different measurements. And there's a very simple, easy way to do it, and it all comes back to x squared plus y squared equals r squared, the equation for a circle, which is kind of the Pythagorean theorem where we had x squared plus y squared equals 1. And remember, we use that for our trig functions, but the reason why we did 1 for the trig functions is because we were doing that when it was on a unit circle. And now we're just going to elaborate to all circles. They don't have to be unit circles. They no longer have to have a radius of 1. So remember that x squared plus y squared equals 1, and then of course cosine squared plus sine squared equals 1, right, by substitution, and SOHCAHTOA. And with those two ideas in mind, we remember that any point in space has both an x distance and a y distance. And if we have an angle, we know that cosine of that angle is always adjacent over hypotenuse, right, from SOHCAHTOA. And then sine is opposite over hypotenuse. And so given this, right, our good old Pythagorean theorem, and the sine and cosine relationships, of course, we also know tangent. We can get tangent from just doing sine over cosine and doing some simple algebra, but you can also just memorize that tangent is opposite over adjacent, the last part of SOHCAHTOA, right? Then these three things along with the Pythagorean theorem is what allows us to name this point two different ways. This point is going to be x, y, but it's also r theta, and we can convert back and forth using these ideas because you see how here's a y, here's an r and a theta, here's an x, here's an r and a theta, here's a y and an x, here's a theta, and then here's a y and an x and an r. So it relates the r's and the thetas, right, to the x's and y's. And so that's what allows us to kind of solve for one given the other and back and forth. Let's look at some examples. So if we want to convert a polar coordinate, r theta, to rectangular coordinates, all you have to do is use the sine and cosine identities, do one simple algebra, right? Get rid of fractions like we always do. First step, get rid of fractions, decimals, grouping objects. So we multiply both sides by r, and we get this lovely rule, right? And then over here, we multiply both sides by r, and we get this lovely rule. And so now, if we're trying to go from polar to rectangular, it's really simple. Because if they tell us this is our polar coordinate, well, remember, this is r, right? This is theta. So all we have to do is stick these things in, right, to those two nice identities, slap it into your calculator, figure out what cosine of theta is, figure out what sine of theta is, multiply them by r, and you get your two numbers for x and y, and then there is your rectangular coordinate, right? The standard Cartesian one that we're used to. Simple. We could do it again with another example, and you can see that it's just the same thing. Very, very easy. Don't overthink it. Just remember SOHCAHTOA and the Pythagorean identity is the two things that help you go back and forth between polar and rectangular. All right, how about going in the other direction, converting from rectangular to polar? Well, you're still using the same identities, right? You're still using the same x squared plus y squared equals r squared, but because now you're trying to find r, you want to solve that equation for r, and therefore you just take the square root of both sides and let r equal the square root of x squared plus y squared. So nothing new there. And then the same thing for the other ones. You had, sine and cosine equaling something over r, right? Y over r for sine, x over r for cosine. But because you want to kind of solve for x and y without having to worry about r, it's better to use the tangent piece. You don't have to, but it's just going to be simpler. So to find theta, given x and y, right? Because remember, the whole idea is you're given a rectangular coordinate and you're trying to find the polar stuff. Well, since you have x and y, it's better to use this formula because you're given two of the three pieces. If you tried to use, for instance, sine of theta equals y over r, well, they give you y, but they don't give you theta and they don't give you r. So unless you did this work first and solve for r, and then plug that in for r, you can't solve for theta, right? Because you just got one equation here and two unknowns. You don't know r and you don't know theta. So if you want to, you can always do this step first, right? Step 2, you can do that step first, and then use that r and use your typical sine and your typical cosine equations. But it's a lot easier to just do the tangent piece, because for all three of these, in order to solve for theta, Don't you have to take an inverse, right? To solve for theta, I got to take inverse sine of both sides. To solve for theta here, I got to take inverse cosine of both sides. To solve for theta here, I got to take inverse tangent of both sides. And it's just as easy to take an inverse of one from the other. So why not make your life simple and just use this one? Because you take the inverse tangent of both sides. So basically, theta will always just equal the inverse tangent of y over x. Now remember, when you take inverse tangent functions, it always gives you answers in specific quadrants, right? Where is the inverse tangent function defined? If you take an inverse tangent, it's always going to give you answers. It's going to give you thetas, right? Angles that are locked in certain quadrants. But that might not be the quadrant that you're dealing with. So if you don't remember, inverse tangent is restricted to negative pi over 2 to pi over 2. So the inverse tangent function, right, only gives you angles in quadrant 1 and quadrant 4, right, from negative pi over 2 to pi over 2. So when you take this inverse tangent, it's always going to give you an answer. It's going to give you an angle that's in one of those two quadrants. Well, what happens if the point you're trying to convert was actually over here or over here? Well, what's going to happen is instead of finding this angle, it's going to give you a reference angle. So you just have to be careful, and that's why step one is always find the quadrant that you're in, from this point, which is pretty easy, right? You just look at the point and go, is the x and y parts positive or negative? And depending on that, it tells you what point you're in, right? If they're both positive, you're in quadrant 1. If x is positive but y is negative, you're down in quadrant 4, and so on and so forth. So depending on what quadrant you're in, you know that you just need to kind of change that based on the answer you get. You're going to get something over here. It's going to give you this angle. And if you need to be in this quadrant, then remember that that's going to be the same angle. So you're going to do 180 minus it, and that's going to give you the angle you're actually looking for when you're switching over to polar coordinates. So really the only tricky part on converting from rectangular to polar is you have to pay attention to your quadrants and make sure that you do the appropriate augmentation to get the correct angle to put you in the correct quadrant. All right, let's look at a couple examples. So here's our first simple example where we're going to convert from rectangular to polar. We're given our two rectangular coordinates. We're given x and y. So we know x equals this, y equals this. We know that r is the square root of their squares, so you do that work really easily and you get r equals 4. Boy, wasn't that nice that they let us have a nice whole number for r. That obviously won't always be the case, but most of the examples we're going to see, r is going to be a nice, pretty integer. But in the real world where this stuff is actually applicable, that's almost never the case. Just keep that in mind. Okay, so we now have r. We also need to determine, we should have done this first, what quadrant are we in? Well, since x is negative and y is positive, right? So x is negative, we're over in this half, and then y is positive. So that means we're somewhere in quadrant 2, right? Negative x, positive y. So quadrant 2. Okay, now that we have found our r, we have to find our theta. Easiest to use the tangent identity. We plug in the 2 bits, we get negative square root of 3. We take the inverse tangent of that, and we get 2 pi over 3. Well, we don't really get 2 pi over 3. It takes a couple. If you actually put inverse tangent, right, because obviously to solve for this, you have to do inverse tangent of both sides, and you get theta equals tan inverse of negative the square root of 3. And if you do that, if you're in degrees, you get negative 60. And if you're in radians, obviously you would get negative pi over 3. So according to our calculators, we're down here at a 60-degree angle, right? That's what negative 60 means. But remember, we're not in quadrant 4, we're in quadrant 2. So instead of being down here, which is pi over 3, right, that's what we've got here. If you think about putting us up here in quadrant 2, because this is where we're supposed to be, so kind of take the line and go in the opposite direction, so this is a straight line. So now this has to be 60 degrees or pi over 3, right? So this angle, which is our theta, because we always try, and unless told otherwise, your theta is always going to be starting at the origin and going in the positive direction. So to get to that line, we have to go around almost to pi. We have to go to pi minus pi over 3, right? Or 180 minus the 60, 120 degrees, right? And so that's where this comes from. We're just saying go to pi and then back up pi over 3, and that's the angle that gets us this line, 2 pi over 3. Or if we go all the way around to 2 pi and then subtract pi over 3, that puts us in this direction, right? So this angle is giving us the line that's facing in that direction. This angle gives us the line that's facing in this direction. And we can really choose either one, because remember, in polar coordinates, we can either walk forward, because this is where we want to be, right? We want to be up here at a point up there. So we can either walk forward on this line, or we can face in this direction and walk backwards. And we already figure out what r was from the previous question, right? It was 4. So if we want to go in the positive direction, we got this one right here. And then if we wanted to go all the way around to 5 pi over 3, which is down here, then we would just have to change that to -4. So we could have a -4 and then 5 pi over 3 would be the other polar coordinate. And then, of course, there are infinitely many ones after that. All right, the third thing we want to talk about, converting equations between rectangular and polar forms. This is probably the thing that you'll use the most if you use polar at all. Polar coordinates in general is a pretty kind of sidebar topic in algebra. You don't see it very often. You don't use it very often. You don't even use it very often in calculus and physics and other classes that you might need algebra for. So if this is really giving you a lot of trouble, don't panic. It's one of those lesser topics that's not the worst thing in the world if you don't perfectly understand. But out of these 4 topics we're going to discuss within polar coordinates, this is the one that you would probably use the most, because converting back and forth between rectangular and polar equations is probably the most useful of the 4 skills. Graphing is definitely the least useful, and we're going to skim through that really quickly. The reason why it's least useful is because just let technology graph for you. Okay, so equations in rectangular and polar form, again, we're just talking about how we normally talk about equations as being things that designate a set of points that are in the Cartesian plane, that are x's and y's. And now we're just going to describe that set of points with polar equations. And the easiest way to do that is to go back to our SOHCAHTOA stuff and use that to relate one to the other. Here are some typical examples of polar equations. And so you can notice that instead of things being in terms of x's and y's, they're in terms of r's and thetas, right? Those become our 2 variables, r's and thetas. So to convert an equation from rectangular to polar form, all you have to do is do the easiest substitution, right? Just you have to remember that, as we saw, again, coming from SOHCAHTOA, that cosine of theta, remember, equals x over r. So with some simple math, r cosine theta equals x. So anytime you see an x in your equation, you replace it with r cosine theta. Do a simple substitution. And then the same thing with y, remember, because that just comes from sine theta equals y over r, and of course with some simple, just multiply both sides by r. You get this equation. So now anytime you see y, you just replace it with that, r sine theta, and then you can get an equation in terms of thetas and r's instead of x's and y's. Simple. So converting from rectangular to polar is really easy. And then going in the other direction is just a little bit less easy, but it's still very easy. Okay, so here's a simple example. Let's convert this equation to polar form. If you don't know what this looks like, it's going to be circular in nature, possibly an ellipse, but most likely a circle of some sort. All you have to do is every time you see an x, put in your r cosine theta. Every time you see a y, you put in your r sine theta, and then do our normal rules, right? Get rid of fractions, decimals, and grouping objects. Grouping objects are parentheses, so to get rid of parentheses, you actually do the squaring, right? So FOIL it out, take the -3 and multiply it through, then get those pieces and see if you can simplify them. You notice, hey, I've got an r squared times a cosine squared plus an r squared times a sine squared. I can factor out that r squared and just get cosine squared plus sine squared. And I remember, because the number one identity we've learned with trig is cosine squared plus sine squared equals 1, good old Pythagoras. And so that makes a nice little simplification. So now we just get r squared. There's really nothing we can do left with this. And so we're stuck with this. I mean, this is what we have left. But I mean, if you look at the original one versus this one, it's not like it's any more complicated, right? So it's 6 and 1/2 dozen the other. They're pretty simple, pretty similar. It's not like one is going to be a lot easier than the other. Sometimes one will be cleaner than the other, and that's why we switch from one to the other. But usually it's just because we need to be working in polar form, so we'll convert that way. Or we need to be working in rectangular form, so we'll convert in that direction. That's really the only main reasons why we convert back and forth. Okay, so if we're going to convert from polar to rectangular, right? So now we're going in the other direction. It just comes back to the big four that we saw before, remembering all of these things. And then the idea is you kind of have to be clever, right? You have to realize that, all right, this is all I have to work with. And I'm going to be given an equation, and that equation is just going to have some r's and some thetas in it. And the idea is I want to turn that equation into something that has nothing but x's and y's in it. So depending on the stuff they give you, that determines, which of these four you use. So for instance, the first one they give us is just r equals 3. Well, out of those four equations, the only one that has just r in it, because remember we don't have theta, is the first one. If we tried to use any of these two, either of these two, and let r equals 3, so we put in a 3 for here, well, that's great, but now our equation is in terms of x and theta, or y and theta, instead of just x's and y's. But if we do it this way, we get everything in terms of x's and y's. And so that's why you would do it that way. And you can see that x squared plus y squared equals 9 ends up being just a simple circle. Okay, the next example, B, they tell us just theta equals something. So again, we look down here and we go, okay, if we use this one or this one, we're stuck with needing to know both theta and r in order to kind of solve this for just y or just x. And over here, there's no theta in it whatsoever. So this is the one to use. So now by substitution, tangent of theta equals tangent of 45, take tangent both sides. And now we have tangent of theta, we swap that in, make it y over x. Y over x equals tangent of 45. If you take tangent of 45, you get 1, so that's why y over x equals 1. Multiply both sides by x. Why? Because our rules tell us get rid of fractions, decimals, and grouping objects to make things simpler. And we just get the simple equation y equals x, which is a straight line that goes through the origin at a 45-degree angle. Oh, well, duh, that's exactly what theta equals 45 is, right? Okay, our third example, we now have r equals cosine theta. Now we have an r and a theta. So when we have r and theta, we should be thinking about using the two middle ones. But neither one of these is cosecant. But what is cosecant but 1 over sine? Again, multiply both sides by sine theta because get rid of fractions, decimals, grouping objects, right? And now we have r sine theta, and you go, oh heck, if I multiply both sides by r, I get r sine theta equals y. This gives me a straight substitution, y equals 1, and y equals 1 is a nice horizontal line at a height of 1. Last but not least, they give us r equals 2 cosine theta, and you go, well, again, I see r and I see cosine theta, so with the cosine theta piece, I'm going to do this substitution, and I'm just going to get 2 r cosine theta, right? What we did here is we multiplied both sides by r because we want to get rid of everything, right? If we just did a substitution here with cosine theta, we would have x over r. So if you don't see this step this way, if you went the other way, you would see it, right? So maybe you can just go, hey, cosine theta is this. I'm just going to do a straight substitution. I'm going to get r equals 2 times x over r, right? Because with cosine theta equals x over r, I just do a straight substitution. And then what's your first rule? Get rid of fractions or decimals. So I would do r squared equals 2x, right? And then, hey, r squared is just x squared plus y squared. So you would do that substitution and you would get right to there. And to me, I think that's a little cleaner and easier way to wrap my head around it. I think that's a simpler way of doing it. So, it's not like there's only one way to do this. Just jump in. You see a cosine theta, use that substitution. You see an r, use that substitution, and so on and so forth. Okay, last but not least, graphing polar equations. Well, actually it's last and least because this is the least important topic out of all of these. And the reason why it's the least important is there's such great technology out there that can graph these things for us. There's really no need to waste a lot of brain power trying to graph things. It's nice to know how to graph them by hand only because it helps you understand the functions a little bit better. It helps you understand how polar coordinates work a little bit better. It's that reasoning for why you would want to try and graph these things. You're not graphing them just to figure out what the pretty picture is. Okay, so it is a good idea to try and graph these things by hand for the learning part of it, but it's not necessary to graph them by hand if you're just trying to figure out what they look like, because that's easier done with simple technology like this great thing. It's the Desmos calculator. It's free. It's an online calculator, so you can use it both with Windows-based machines, Mac-based machines, and Android-based machines. There's actually a version of it available in the Google Play Store that's also free, that you could install it as an app on any of your Android devices, and then you could graph things using your phone or a tablet. I'm going to show you here on my PC. Here it is. You won't see everything just because I'm kind of zoomed in from the previous slides, but if I make this smaller and bring it down here so we can see what's going on, you can see that all you have to do is type in your polar coordinates. So let's say r equals 3. See how I got the orange circle? Let's say I wanted to do one of these, what they call the rose curves. I can do r equals, how about 3 cosine, how about 5, and then we go in here and put in theta, and there it is. See how we get 5 petals? So it's really easy to graph with this tool. It's really cool and simple, and makes it a lot easier than having to do things by hand. If you wanted to worry about what this stuff means, we're just graphing things in terms of a set of points that are defined by r and theta instead of a set of points that are defined by x and y. So it's really nothing different, right? There are certain things that can help us speed up the graphing process. We can look for symmetry with respect to the x-axis. We can look for symmetry with respect to the y-axis, or when theta equals pi over 2. We can look for symmetry with respect to what we call the pole, which is really the origin. So things that are symmetrical, in opposite directions from the origin. And once we know symmetry, then it kind of narrows down the number of points that we have to plot in order to find more points. If we know something's symmetrical, we just plot all the points on one half, and then we know we get the other half from symmetry. So that's what this example is. We plot these points, we use some symmetry, and we know that we get this funny little shape here, which is called a cardioid because it kind of looks like a heart. Here's another one where we can use the test for symmetry, plot some points, right? Plot some more points, start figuring out what they look like. Go, oh, we've got symmetry, so from here, we know that we get symmetry over the x-axis, symmetry along the y-axis, and all of a sudden we get this little like four-leaf clover looking thing, and it's called a four-leafed rose. I don't know why they call them roses instead of clovers, maybe because roses have more than four petals. I don't know. There's these limicons or limicons, depending on how pretentious you are and how you want to pronounce it. They basically look like cardioids, but the dimple changes. You can have a dimple, you can have a loop, you can have kind of a shallower dimple, no dimple at all. Then you've got the different rose curves where you just have different numbers of petals. You can do circles that are either centered at the origin or not centered at the origin. You can have these lemniscates, which look like infinity symbols. And then you can have spirals. Those are kind of the general families of graphs. Again, I went through them quickly because I don't think graphing is really important. Hopefully the other stuff sticks. Being able to convert back and forth is really important, and especially being able to convert back and forth with equations. All right, that's everything we're going to need to know about polar coordinates.